In 1927, during a series of experiments that still haven't been fully explained, physicists discovered something that should have rewritten everything we thought we knew about reality. The experiment was simple in its design, deeply unsettling in its implications, and has never been satisfactorily resolved in nearly a century of subsequent investigation. A beam of particles, electrons or photons or any quantum scale object, was fired at a barrier containing two narrow slits. Behind the barrier, a detection screen recorded where the particles landed. When no one measured which slit each particle passed through, the particles behaved as waves, producing an interference pattern across the back screen, as though each particle had somehow passed through both openings simultaneously. Any instruments were placed at the slits to observe which path each particle actually took. The interference pattern vanished entirely. The particles began behaving like ordinary objects, passing through one slit or the other, landing in two corresponding bands on the screen. The act of measurement, the simple fact of looking, had changed the physical outcome of the experiment. Not the equipment, not the interference, the looking itself. This is what physicists call the quantum measurement problem, and it is not a fringe interpretation or a theoretical curiosity. It is a documented, reproducible feature of reality at the subatomic level. Particles do not exist in a single definite state before measurement. They exist in superposition, occupying every possible configuration simultaneously until the moment an observation forces a specific outcome to emerge. The technical term for this is wave function collapse. What it means, stripped of the mathematics, is that a particle has no fixed position, no fixed momentum, no fixed spin until something measures it. Before that moment, it is genuinely, physically, all of those things at once. The simulation theorists who cite this experiment are not reaching. Consider how a modern video game engine handles its world. It does not render every room, every corridor, every patch of landscape simultaneously. It renders only what the player's camera can currently see, calculating the visible geometry on demand and discarding the rest. This is not a stylistic choice, and it is an engineering necessity. Maintaining the full state of an entire rendered world at all times would be computationally catastrophic. The system calculates what it needs, when it needs it, and only when something is looking. The parallel is not subtle. A universe that declines to assign definite properties to its particles until those particles are observed is behaving, structurally, like a system that renders on demand. The processing cost of maintaining every particle in every possible superposed state across the entire observable universe simultaneously would be extraordinary. Consciousness-triggered collapse, in this framing, is not a mystery to be solved. It is an optimization strategy. Reality computes the answer when the query is submitted, and not a moment before. The question, then, is not whether this resembles a computational process. The question is whether the resemblance is coincidental, and if the universe only decides what something is at the moment you look at it, then what exactly is it doing when you're not? At a certain point, space itself stops making sense. That boundary has a name, the Planck length, approximately 1.616 times 10 to the negative 35 meters. A unit so incomprehensibly small that if an atom were scaled to the size of the observable universe, the Planck length would still be smaller than the atom itself, and below which, according to every theoretical framework physics has so far produced, the concepts of distance, position, and spatial measurement simply cease to function. Not because our instruments aren't precise enough to detect what lies beneath, but because the mathematics that describe reality at that depth indicate that space itself has no further subdivisions to offer. Nothing smaller exists, nothing smaller can exist, and the universe at every scale above that floor gives no indication of why this particular threshold was placed precisely where it was. It should be strange because, in almost every other observable respect, the physical universe behaves as though it is continuous, as though matter and energy exist along unbroken gradients that could theoretically be subdivided further and further without ever reaching a bottom. And yet at the Planck scale, that apparent continuity simply ends, replaced by what physicists can only describe as a hard minimum unit, a resolution limit, a floor beneath which reality won't go, and which calls to mind, with uncomfortable precision, the fundamental constraint of every digital display ever built. A pixel is the smallest unit of the image, The grid can't be subdivided further, and no matter how closely the screen is examined, nothing finer exists beneath the rendering layer. Scientists at the University of Bonn examined the behavior of ultra-high energy cosmic rays. Particles accelerated to velocities approaching the speed of light, crossing billions of light years before striking Earth's atmosphere, and found that these particles appeared to move as though constrained by an underlying computational lattice, as though space weren't a smooth and uninterrupted medium through which matter flows freely, but a structured grid with fixed intervals governing how energy and matter could propagate. A finding that existing models of physics struggled to accommodate, and that was never in any widely circulated official capacity fully explained. No formal model was offered to account for what the data appeared to show. The implication that space itself might be discrete rather than continuous, structured rather than smooth, a lattice rather than a fluid, was left sitting in the literature without resolution. Then came James Gates. A theoretical physicist at the University of Maryland, Gates was working within the mathematics of supersymmetry, the framework constructed to reconcile quantum mechanics with the behavior of fundamental particles at the deepest level of physical description, when he found something embedded in the equations that had no business being there. Error-correcting codes, the precise class of self-checking algorithms used to maintain data integrity in digital systems and web browsers, structured identically to those codes, functioning in the same manner, woven into the mathematical description of how the universe actually works. Not as a loose analogy or a metaphor, but as a genuine and verifiable structural feature of the equations that govern reality. When the laws of physics contain the same error-correcting codes that run your web browser, the word coincidence starts to feel insufficient. In 2009, a paranormal researcher named Fiona Broom posted something online that accidentally broke the internet's sense of reality. She had carried for years a vivid and specific memory of Nelson Mandela dying in a South African prison during the 1980s, a memory that came complete with news coverage, a widow's televised address, and the kind of emotional texture that only attaches to events genuinely witnessed. And what she found upon sharing it publicly was not a chorus of gentle corrections, but thousands of responses from people who carried the exact same memory, the same funeral, the same speech, the same decade. Despite the inconvenient fact that Mandela had walked out of Robben Island in 1990, had governed South Africa as its first democratically elected president, and had died peacefully at home in Johannesburg in December of 2013. She called it the Mandela Effect. Dozens of examples followed, but none has proven more resistant to dismissal than the one involving a children's book series that has been printed, purchased, and placed on bedroom shelves since 1962. A series known to millions of readers as the Berenstain Bears, named for its authors Stan and Jan Berenstain, and spelled with an A in the final syllable, a fact that a remarkable proportion of adults find impossible to accept, because their memory, clear and confident and repeatedly reinforced across years of childhood reading, tells them the name ended in E, that it was always Berenstain, and that whatever the covers currently say, that is not what the covers used to say. Neuroscience has an answer. Reconstructive memory doesn't retrieve stored recordings, but rebuilds them each time from fragments. And during that rebuilding process, schema filling substitutes plausible detail for missing content, source misattribution confuses the origin of knowledge with its substance, and social reinforcement causes a false version to calcify until it becomes experientially indistinguishable from the truth, with formal studies confirming that 76% of subjects make significant errors when asked to recall specific details of events they experienced firsthand. That framework accounts for why memory fails, but not for how it fails uniformly. It does not explain collective convergence. The fact that when memories fail in these documented cases, they do not scatter across a range of plausible alternatives, the way random reconstruction errors would predict, but instead collapse onto a single specific incorrect version with a consistency that makes statistical coincidence increasingly difficult to argue, as though the wrong answer is not being independently generated by each person who gives it, but retrieved from somewhere that many people are quietly accessing without knowing it. The simulation framing for this is both straightforward and unsettling. A patch was applied, the record was corrected, the current version of the file reads as it was always meant to read, but the memory cache belonging to those who loaded the previous version was not wiped cleanly, leaving them in possession of something that no longer exists in the official record. A residue of a prior state, a fragment of overwritten data that is persistent and specific, and shared by people who have no explanation for why they all remember something that, by every measurable standard, never happened. What's hard to explain isn't that people misremember. It's that when they do, they misremember the exact same thing. Every person reading this has at some point been struck by the sudden and overwhelming sense that they have already lived the exact moment they are currently inside. The conversation, the angle of light through a window, the specific arrangement of objects on a table, all of it achingly, impossibly familiar, and yet entirely impossible to locate in memory. It lasts only a few seconds. Then it dissolves. And the world continues as though nothing happened. Neuroscientists have studied this phenomenon for decades, producing explanations that are technically coherent and somehow insufficient. The leading theory involves a misfiring within the temporal lobe, specifically a breakdown in communication between two distinct memory systems, one responsible for recognizing familiarity and one responsible for retrieving the actual source of that familiarity. When the recognition system fires without the retrieval system confirming a real memory, the brain registers something as known without being able to explain why. The result is that specific, disorienting sensation, the certainty of repetition with no evidence to support it. No prior event, no retrievable source. Just the feeling, arriving uninvited and departing without explanation. Approximately 2/3 of the population reports experiencing it. That figure, drawn from multiple independent surveys, is striking on its own. But what is perhaps more striking is the consistency of the experience across those reports. Déjà vu is not described differently by different people. It does not present as a vague unease or a general sense of familiarity. It presents as the same specific sensation every time in every person, the feeling of a moment being repeated. The neuroscience accounts for the misfiring. It does not fully account for the uniformity. In 1977, at a science fiction convention in Metz, France, the writer Philip K. Dick stood before an audience and said something that the scientific community mostly ignored and has never entirely been able to dismiss. He claimed with considerable conviction that we are living inside a computer-programmed reality, a constructed environment maintained by an external intelligence, and that the only reliable evidence available to us of this fact arrives in moments when a variable within the program is altered. When something is changed, adjusted, corrected, or rerun, the alteration leaves a trace. Not in the physical world, where the update would appear seamless, but in the experiential record of those inside it. The previous version of the moment leaves a residue. The simulation framing does not require the neuroscience to be wrong. The temporal lobe misfires. The recognition system triggers without a source memory. That is all accurate. But the question the simulation framing raises is what precisely the recognition system is detecting. Because if a moment has been rerun, corrected mid-execution, or restored after a patch, the prior instance of that moment would exist somewhere in the experiential record, just beyond the reach of retrievable memory, close enough to register as familiar, too altered to be found. The brain did not invent the feeling, it noticed something, and it has no framework to explain what. Philip K. Dick put it simply, it's not a brain error. It's a timestamp from the last time the scene was run. Carl Jung spent decades collecting stories that he couldn't explain and didn't try to dismiss. A patient describes a vivid dream about a golden scarab beetle, and at the precise moment she recounts it during a session, a scarab-like insect strikes the window of Jung's consulting room. An event so geometrically unlikely, occurring in a city and climate where such insects almost never appear, that Jung himself documented it as one of the foundational cases for what he would eventually call synchronicity, a term he introduced not as metaphor but as a formal principle. The meaningful coincidence of events linked by significance rather than cause. He declared in his essay on the subject that the cases demanding his attention involved spontaneous convergences of such improbability that to classify them as coincidence required a definition of coincidence willing to absorb nearly anything. The experiences Jung cataloged are recognizable to almost everyone who has encountered them, even if the language for them tends toward the dismissive. A person thinks of someone they haven't spoken to in years, and the phone rings within minutes. A stranger at a gathering volunteers a precise detail about a subject the listener has been privately wrestling with for weeks, without any possible means of knowing it was relevant. A book, taken at random from a shelf, falls open to the single passage that addresses exactly the question currently unresolved. Not approximately, not thematically, but with the kind of surgical specificity that resists easy accounting. These events share a structure. The external world appears to respond to an internal state, as though the boundary between mind and environment briefly dissolved, or was never there to begin with. The standard objection is well constructed and deserves acknowledgement. Human cognition is demonstrably prone to pattern recognition. Confirmation bias amplifies the emotional weight of matches while quietly erasing misses. And in a world generating billions of daily interactions, statistically improbable events must occur constantly simply by volume. But Jung's documented cases and the verified cases that followed in clinical and investigative literature complicate that dismissal in ways the statistical argument does not cleanly resolve, because some of these synchronicities involved multiple independent witnesses, verifiable timestamps, and a degree of informational specificity that transforms probability calculations from uncomfortable to genuinely intractable. Situations where the CI convergence is not merely surprising, but structurally impossible to assign to noise without straining the framework past its tolerances. The simulation framing offers a different architecture entirely, and it is one that treats synchronicity not as a failure of statistics, but as evidence of something seeping through the rendering. Moments where the system organizing experience reveals, however briefly, that it is organized, that events are being arranged rather than merely occurring, that what presents itself as physics is occasionally behaving more like plot. If the universe were a narrative system with scripted elements embedded beneath the surface of apparent randomness, synchronicities are precisely what the seams would look like from the inside. Places where causality gives way to meaning, where the machinery shows through the scenery. A universe with no author shouldn't have themes, and yet somehow it keeps producing them. In 1901, a sponge diver working off the Greek island of Antikythera pulled something out of a shipwreck that no one in the scientific community could explain for the next 50 years. What emerged from that corroded bronze mass, after decades of painstaking analysis by researchers at the National Archaeological Museum in Athens, and later by imaging teams using X-ray tomography, was a fully operational astronomical computer. A device containing at least 30 interlocking differential gears, calibrated to track the movements of the sun, the moon, and 5 planets across a 19-year metonic cycle, predict solar eclipses and calculate the timing of the ancient Olympic Games, with a mechanical precision that engineers today describe as not merely impressive, but structurally impossible for the period in which it was built. The shipwreck has been dated to approximately 65 BCE. The next known mechanism of comparable gear complexity does not appear in the historical record for another 1,400 years. It is a rupture. What makes the Antikythera mechanism so difficult to absorb is not that an ancient civilization was ingenious. It is that the specific technological leap it represents left no trail, no predecessor devices, no progression of prototypes, no evidence of the accumulated engineering tradition that would ordinarily be required to produce such an object, as if it arrived complete and fully realized into a world that had not yet learned the intermediate steps. In the temples of Dendera in Upper Egypt, carved into limestone relief panels dating to roughly 50 BCE, a set of images depicts figures cradling elongated, serpent-filled vessels that a subset of electrical engineers and historians of technology have argued bear an unsettling structural resemblance to early Crookes tube filament lamps. Ahash this. Lotus flower pedestals functioning as insulators, the serpents as illuminated filaments suspended within a glass envelope. Egyptologists dispute the interpretation. The resemblance, however, is not vague. In 1898, excavators clearing a tomb at Saqqara recovered a small carved object made of sycamore wood, shaped unmistakably like a bird, with a vertical tail fin and wings angled in a precise dihedral configuration that aeronautical engineers who later examined it confirmed would generate meaningful lift at the correct airspeed. A functional glider, built and buried in a civilization that, according to every conventional account of the historical record, had no concept of heavier-than-air flight, no theoretical framework for aerodynamics, and no known cultural context that would explain why such a design was produced with such structural accuracy. The object sat in a Cairo museum storage box labeled wooden bird toy for decades, before anyone with an engineering background examined it close. The framework that simulation theorists apply to objects like these is precise. If the history of a constructed world was assembled rather than evolved, there would be inconsistencies. assets rendered into the wrong era, test objects embedded in the environment and never retrieved, moments where the data describing the past failed to align perfectly with the intended sequence of events. The same way a video game world occasionally surfaces a developer object in a location a player was never meant to reach. Each of these artifacts carries its own conventional explanation, and each of those explanations requires accepting that the object in question simply arrived, complete and anomalous, with no traceable origin and no descendants. The question isn't just how they existed, it's whether the timeline they were found in was ever supposed to contain them. In 1935, Albert Einstein published a paper designed to prove that quantum mechanics was incomplete, and instead accidentally described one of the strongest arguments for simulation theory ever written. The paper, co-authored with Boris Podolsky and Nathan Rosen, was meant to expose a fatal flaw in the emerging framework of quantum theory. Specifically, the idea that two particles, once interacting, could remain permanently linked regardless of the distance subsequently placed between them, such that measuring the state of one would instantaneously determine the state of the other, not after a signal had time to travel, not after some hidden mechanism had time to operate, but at the same moment, across any distance whatsoever. Einstein found this conclusion not just implausible, but philosophically intolerable, describing it as spooky action at a distance, a phrase that was meant to discredit the theory by making it sound absurd. It was a feature of physical reality that no framework B, built on conventional physics, had any satisfying mechanism to explain. In 1964, physicist John Stuart Bell devised a mathematical framework, now known as Bell's theorem, that could determine, through measurable statistical distributions, whether entangled particles were truly influencing each other instantaneously or whether they were instead carrying hidden predetermined information from the moment of their creation, information that merely appeared to correlate because it had been set in advance, like two envelopes sealed with matching letters rather than two letters that somehow rewrote themselves mid-transit. The experiments that followed, most decisively those conducted by Alain Aspect in the early 1980s, and later refined with increasing rigor through the 2010s and into the present decade, returned a consistent verdict. The hidden variable explanation was wrong, the correlations were real, the connection was genuine, and no classical signal of any kind was responsible for carrying the information between the two particles. The speed of the correlation is the thing that refuses to resolve cleanly, because in a universe governed by the principle that no information can travel faster than light, a constraint so fundamental that its violation would unravel causality itself, the instantaneous coordination of entangled particles located at arbitrary distances from one another should be impossible, and yet it is reproducibly, experimentally, inescapably real. This is the point at which the simulation framing becomes difficult to dismiss without effort, because in any computational system, two variables linked to a shared memory address do not need to communicate across space. They need only to be read, and what is stored at that address is already the same for both, instantaneously, not because a signal connected them, but because they were never separate in the architecture of the system, only in the apparent geography of the world the system renders. It was always there, written once, accessed twice. It is one of the very few arguments drawn from simulation theory that practicing physicists have found worth modeling in formal terms rather than dismissing outright. And the reason is simple. Nothing in standard physics explains why the correlation is instantaneous, but in a system built from shared data structures, the question of why dissolves entirely because there was never anything to transmit. In a physical universe, two particles separated by 1 billion miles shouldn't be able to share a state. But in a database, they already do. The universe should not exist. The gravitational constant, the cosmological constant, the charge of an electron, the precise ratio of electromagnetic force to gravitational force. Each of these values is calibrated to a specific numerical setting, and if any one of them were shifted even fractionally in either direction, the result would not be a slightly different universe, but no universe at all. No stars capable of igniting, no atoms capable of bonding, no chemistry capable of producing the molecular complexity that life requires, and no passage of time long enough for any of it to matter. Physicists who have studied the problem describe it in terms that are difficult to absorb without unease. The cosmological constant alone is tuned to a precision of 1 part in 10 to the power of 120, a number so large that writing it out in full would require more digits than there are atoms in the observable universe. The standard response from the scientific community is the multiverse. an infinite or near-infinite proliferation of universes, each governed by a different combination of physical constants, with the overwhelming majority being sterile, cold, structureless, and dead, and ours being simply the one that happened, by chance, to draw the correct configuration. It is a serious hypothesis. It has theoretical grounding in string theory and inflationary cosmology, and it addresses the fine-tuning problem by removing the need for probability calculations altogether. If every possible setting exists somewhere, then the fact that we inhabit the one that works requires no further explanation. But the multiverse remains untestable, unfalsifiable, and by the standards of empirical science, invisible. The simulation framing requires none of that. It requires no infinite proliferation of dead universes, no appeals to anthropic selection across a cosmic lottery that no one can verify. It requires only a programmer, someone or something, that examined the parameter space, identified the configurations capable of producing complexity and consciousness, and entered those values deliberately before running the process. The anthropic principle, which holds that we should not be surprised to find ourselves in a universe hospitable to life, because a universe inhospitable to life would contain no observer to register the fact, addresses the logical puzzle without addressing the engineering one. It explains why we are here to notice, but it does not explain why the dial was set correctly in the RST place, and those are not the same question. But what makes the fine-tuning problem genuinely difficult to dismiss is not the precision of any single constant, but the convergence of all of them simultaneously, calibrated in concert, in a way that produces not merely life, but the specific layered conditions: stable matter, nuclear fusion in stars, carbon chemistry, electromagnetic radiation at frequencies that biological processes can use, that any designer capable of constructing a universe from a specification sheet would have been required to input before activation. The anthropic principle tells us we would not be here to ask the question if the answer were different. It does not tell us why the answer is what it is. The difference between a universe that accidentally supports life and one that was built to support it is invisible. From the inside, which is exactly the problem. 3 days before Abraham Lincoln was assassinated, he described seeing his own face staring back at him from an empty mirror, except the reflection looked pale, almost dead. He told the story to his wife, Mary Todd, and to close members of his staff, recounting how the double image appeared briefly and then vanished, leaving one face sharp and living and the other colorless, drained of something he couldn't name. And Mary Todd, by multiple accounts, interpreted the vision immediately as a death omen, a premonition delivered through the glass with a clarity that ordinary dreams rarely managed. Lincoln was not a man given to superstition, and yet the account was recorded, repeated, and never formally disputed by anyone present in those final days before Ford's Theater. The German word itself, doppelganger, meaning double walker, did not emerge from fiction but from folklore dense enough with reported encounters that it required a name, and the cultural consensus across centuries of European tradition was consistent and grim. To see your own double moving through the world meant that your death was near, that something in the order of things had fractured in a way that could not be repaired, and the accounts clustered not around the eccentric or the disturbed, but around figures whose testimonies carried weight: writers, politicians, soldiers, people whose credibility made dismissal inconvenient. Guy de Maupassant, the French writer, documented in careful detail the experience of watching his own figure enter his study, lower itself into his chair, and begin dictating sentences back to him, a scene he described with the clinical precision of a man trying to outrun his own terror by recording it accurately, and he did not survive long after. What makes these cases resistant to easy explanation is not the frequency of the reports, though that frequency is itself uncomfortable, but the specificity of the duplications involved, because in a significant number of documented encounters, people who knew the original person well, intimately for years were briefly and genuinely deceived, unable in the first moment of contact to distinguish the copy from the source. And that level of precision is not what randomness typically produces, not what the ordinary noise of human perception and faulty memory tends to generate even under stress, even in poor light, even at a distance that might excuse some confusion between two people who merely resembled each other from across a room. In a system generating distinct visual identities for millions of simultaneous instances, the engineering problem of infinite uniqueness becomes, at a certain scale, a resource problem. And the most efficient solution to a resource problem in any computational architecture is reuse, partial or complete recycling of existing models, applied to new instances without the expectation that anyone would ever place them in the same location at the same time, and notice the overlap. And yet, occasionally the overlap is noticed, documented, and left without an explanation that satisfies everyone who examines it closely enough. Whether that's a statistical inevitability or a recycled asset depends entirely on what you think reality is built from. Every simulation ever built has a speed limit, not because the programmer chose one arbitrarily, but because every computational system has a maximum rate at which it can process and update information. The universe has one too, 299,792,458 meters per second. A constant so precise and so absolute that Einstein restructured our entire understanding of space and time around it. Not as a ceiling that matter bumps against, but as a fundamental property woven into the geometry of reality itself. A limit so deep that exceeding it doesn't merely violate physics, but renders the concepts of sequence, causality, and existence geometrically undefined. Nothing outpaces it. No signal, no force, no information of any kind has ever been observed exceeding it. And according to every verified physical theory, nothing ever will. In any computational system, whether a processor rendering a city block in real time or a distributed network propagating changes across a shared database, the rate at which information can move through the system is constrained by how fast the underlying hardware can execute operations, and once that ceiling is reached, nothing inside the system moves faster. Not because a physical law prevents it, but because the architecture itself does. The speed of light framed this way is not a cosmic rule. It is a throughput limit, the maximum rate at which the simulation can calculate new states and push those changes outward through the grid. The connection grows harder to dismiss when the Planck length and Planck time are placed side by side. The Planck length, approximately 1.616 times 10 to the negative 35 meters, is the smallest meaningful unit of space. Below it, distance loses physical significance entirely. And the Planck time, approximately 5.39 times 10 to the negative 44 seconds, is the smallest meaningful unit of time, the interval below which temporal sequence becomes undefined. And when these two constants are divided against each other, the result is precisely the speed of light, as though the resolution floor of space and the tick rate of time were not discovered independently from separate physical principles but calibrated against each other, locked together the way a frame rate and a propagation cap are locked together in any game engine running at the edge of its processing budget. A design signature, not a derivation. Engineers who build simulated environments know this constraint intimately. When the ceiling is reached, the world does not slow down. No instrument across more than a century of increasingly sensitive measurement has detected anything exceeding 299,792,458 meters per second. Every attempt confirms the ceiling holds, perfectly, everywhere, without a single registered exception. That consistency is either the signature of a universe whose geometry naturally enforces this limit as an emergent consequence of its own physical laws, or it is the signature of a system that has never once been permitted to exceed its own processing cap. A universe with a hard ceiling on how fast reality can change is either the most elegant accident in existence, or it's running as fast as it's allowed to. These 10 anomalies, scattered across physics, neuroscience, cosmology, and documented human experience, do not form a random collection of curiosities. Each one, examined in isolation, carries a conventional explanation. Quantum superposition is simply the nature of subatomic matter. The Mandela Effect is reconstructive memory behaving predictably under social reinforcement. Déjà vu is a misfiring familiarity signal in the temporal lobe. Fine-tuned constants are either anthropic necessity or the product of a multiverse so vast that every configuration eventually occurs somewhere. And the Planck length is merely the boundary at which our measurement tools become meaningless, rather than a boundary at which reality itself dissolves into something structured and deliberate. AC dismissal is not any individual anomaly. It is the architecture of the pattern they collectively describe. A universe that consistently behaves as though it possesses resolution limits below which detail is withheld, processing constraints that cap the rate at which information can propagate, memory systems prone to specific and repeatable corruption, and fundamental parameters set with a precision that suggests configuration rather than accident. Parameters dialed to values that permit complexity, chemistry, and consciousness, as if someone ran the numbers in advance and entered them carefully, one by one, before initializing the system. What it does constitute is a framework, and that framework is not a new one invented to explain these anomalies away. It is the same framework engineers, developers, and programmers use every time they build a digital world, complete with resolution limits, processing ceilings, error-correcting code, and deliberately configured starting conditions. And if we are inside a simulation, the most disturbing truth isn't that someone built it. It's that we've spent centuries reverse engineering the code without ever asking who's running it.